Welcome to Data Science with EJD. We are still on supervised learning, and particularly we've been talking about clustering. Supervised learning being a branch of machine learning that deals with, uh, you know, machine learning from unlabeled data. So, and all the learning is about categorizing, discovering patterns and things like that, as opposed to supervised learning, which involves working with label data with some inputs, otherwise called targets, and outputs. I mean, some inputs otherwise called features and targets called outputs. So here we are taking a type of clustering model called the Gaussian Mixture Models, GMM. So, by way of introduction, clustering, of course, is an unsupervised learning technique used to group similar data points. So we've taken quite a number of clustering, algorithms like DB-scan in the last case, and before that we did hierarchical clustering. We also did K-means clustering. So clustering is an unsupervised learning technique used to group similar data points. The most common methods include K-means clustering, which is a kind of hard clustering, while Gaussian mixture models, GMM, is a kind of soft clustering. And to explain that again, talking about hard versus soft clustering, clustering, in hard clustering, each point belongs to exactly one cluster, e.g. in K-means now. Then for soft clustering, each point belongs to all clusters with certain probabilities. So if they have, so every data point that is belongs to every cluster with a certain degree, with a certain probability. That's basically what soft clustering is about. And of course, you can understand hard clustering being, you have data points clearly belonging to a well-defined cluster. I mean, to a clear cluster, not overlapping, right? So now let's talk about the Gaussian mixture model, which is the main reason for this video. So a Gaussian mixture model represents the data as a combination. So the data is a combination or mixture. That's where the mixture comes from, of multiple Gaussian or normal distributions. All right. So we have a mixture of normal distributions. So each, of course, Gaussian distribution is normal distribution, and that's a quite popular distribution. In fact, we've always talked about it. We talked about normalizing data and things like that. So, and of course, in statistics, the normal distribution is more like the state of the art, so to speak. So each Gaussian component is defined by a mean vector. You have a mean vector mu k. You have a covariance sigma k. Yeah, we can say sigma k, right? And you have a mixing coefficient pi sub k, such that the sigma from k equals 1, small k equals 1 to big k equals pi sub k. All of that is equal to 1 for the mixing coefficient. Then when we talk about the mathematical formulation, of course, we know that the whole idea of machine learning, AI, and all that is heavily built on mathematics, even when you talk about natural language processing, because they get to talk about things like cosine similarity and all that. It's all maths. So mathematical formulation, the probability of a data point xi, so you have several data points, right? The probability that a particular data point xi is given by the probability of a data point xi is given by p of xi equals summation from small k equals 1 to big K of pi of k dot n, uh, such that xi with a particular mu k and summation and sigma k, that this is what the probability is given like. So probability of xi is that expression, where this part now is the multivariate Gaussian distribution. So this part is a multivariate Gaussian distribution. Multivariate in that you're talking about several data points. So you can have x1, x2 up to xn. On the other hand, okay, of course, that multivariate Gaussian distribution is given as this. So this looks like the typical, okay, it looks a bit like what we know as the expression for normal distribution, except for a few variations here and there, because it is also multivariate, right? So soft clustering using GMM now. GMM performs soft clustering by assigning probabilistic memberships of each point to each cluster. So each point belongs to each cluster. That is what clustering is about. So for a data point xi, we compute the responsibility. So we have responsibility gamma sub ik equals p, probability that of a particular cluster k. So given that you have a data point xi, right? This y gamma sub ik tells us how much component k is responsible for data point xi. Now we go ahead to talk about expectation maximization. That's the EM algorithm. The expectation maximization algorithm is an iterative method used to estimate the parameters of a Gaussian mixture model. I mean, under linear programming, numerical optimization techniques, and even numerical analysis, we've done a whole lot about uh, iterative processes, right? So that can help us understand what's happening here. So we talk about the expectation maximization algorithm, EM algorithm. So first thing is we talk about initialization. So you have to choose the initial values of your means. So the mu k's, mu1, mu2 up to whatever, and the covariances, covariance matrices, sigma 1 to up to a particular value. Then you have the mixing coefficient, the pi sub k, such that we have the summation of everything to be equal to 1. Then, so since you're talking about expectation maximization, so what about, let's talk about the E step, which talks about the expectation, right? So we need to calculate the responsibilities gamma sub ik, which represent the probability that point xi belongs to component k. All right, so we have gamma sub ik equals all this. So pi sub k multiplied by the normal distribution, and then this summation down here, where this, of course, as we know, is the multivariate Gaussian probability density function right now. Then that's the expectation part. Expectation, deals with probability. And then we go ahead to talk about the maximization aspect of things. So here we update the parameters using the responsibilities. So effective number of points assigned to cluster K will now be n sub k equals summation of all the gamma ik's from I equals 1 to n. Then you update the mean mu k is 1 over nk, summation of gamma sub ik multiplied by xi. Then you update the covariance also. We have sigma k equals summation equals 1 over nk and all that. Then update mixing coefficient. You have pi sub k equals nk divided by n. Then the convergence now. So repeat the E and M steps until one of the following conditions is met. So because at the end of the day, since for iterative processes, right, you either probably so you are looking forward to convergence where a particular condition is met. So you repeat the expectation and maximization steps until one of the following conditions is met. The log likelihood converges. That is, changes very little between iterations. I mean, that's the kind of thing we get in numerical analysis. Once the difference within consecutive iterations becomes very small, then you can already begin to think that the solution is there. So the change in parameters is below a predefined threshold. So those are two conditions for convergence. So let's talk about the Python implementation. So using scikit-learn on the iris dataset, that's what we're doing here now. Of course, line 1 to 5, because we have a kind of comparison with k-means clustering. So we need to use line 1 to 5 to suppress a particular error that shows talking about the MKL memory leak on Windows. So then, of course, you import the necessary library. Scikit-learn is it all the way, and then we need matplotlib for visualization. So you need the iris data set, Gaussian mixture, that's our model, standard scalar for pre-processing, and PCA for visualization. To PCA is principal component analysis, which is actually what we're going to see when we. I mean, in fact, this is the last video for now under clustering. So from the next video, we'll be talking about dimensionality reduction, and PCA is one of the things you get to talk about under dimensionality reduction, but we need it here, to visualize. So here we have we load the data. We've done this a couple of times. So iris is load iris, x is iris data. So in this case, because we're dealing with unlabeled data, we don't need y, because we just need x, because we're only going to discover patterns, groupings of x and things like that. So I mean, in previous videos we had y, just not because of the model, but because for some other reasons. I mean, for to serve as a standard or something like that. Then we have to standardize, use this scalar, because we want our data to be normally distributed, right? So we use the scalar. So instead of just using the directors, we need to now use the x scaled, and we get all this. Then we apply PCA for visualization, not the analysis itself now, but just to help us visualize. So we have x, the PCA of x now. So we have PCA n components. We use two components for the PCA, so we can have x1, x2. Then we feed transform x scaled. So the scaled PCA. So we have the normal X, we scale the X, and then we do the PCA for that X, right? For that X scaled. Then we go ahead to fit the Gaussian mixture model. So GMM now is Gaussian mixture n component. So three components for that. Random state is zero. So GMM.fit of the X scaled, and then we label GM predicts. So here now we are trying. This is us trying to predict how how the model performs, you know. So then we now plot the clusters here. Of course, PCA becomes useful at this point. So we have the XPCA. You see, it's strictly for the purpose of visualization. So it's not the analysis itself. So so I run this now. And then this star tells you it's still running the asterisk, but now it's done. So we have the GMM clustering on Iris dataset. So we have the blue clusters, the brown clusters, and the yellow clusters. I think this should be this almost like brown or purple or something like that, or indigo. I don't know. So we have this visualization right here, and that is happening because we chose, I believe, we chose three clusters, components. So what if we make it just two? Let's see what happens. So like I said, yeah, I mean, because we chose two now, we have just these two clusters. So we have the merging of a party of two groups that we had in the previous case. Okay, so um, okay, so this is okay. I didn't change it. It's oh, okay. This is two. Three wouldn't work here, right? So we have two for PCA, but three for the components of this. Yeah, so now this is what we get. So when we used to, these two actually got together like that. So these are the things. So you have PC1 here and PC2 like that. Then how about we do some manual implementation of expectation maximization? And here we're using a two-dimensional synthetic data, like in the other in a previous video we had, I mean, the first case of k-means clustering, we used we made blobs like synthetic data to do some stuff. So that's the kind of thing we are doing here. Having used Iris data here, we want to do synthetic data that gives a more that looks more perfect, but I mean it's just synthetic, it's made up data. So X generator, we have X comma underscore make blobs 300 samples, three centers, random state is 42. So you can play with this, you can change these values you see, and then to see what happens. By the way, you have access to all this my code sheet and my data sets. Just look at the link in the description for YouTube or Facebook, and then it takes you to the Google Drive where you can download all of these things. So for this now, manual implementation of expectation maximization. So using two-dimensional synthetic data. So NumPy, Matplotlib, from the data set we are making blobs, and then we generate data, and we have this. So initialize, you have random seed, since you're making up the data, right? So you have move, which is X with the random choice and all that. Sigma, you have all this. Pi, you have all this. Now, these are some of the variables we've talked about previously, right? And pi is like so ones of k over k like that. So you have multivariate Gaussian, which you define using a Python function now. So we need x, mu, and sigma. So size is x shape 0. Determinant, I think, det, np, linear algebra, dot det, sigma. That's from NumPy for sure. So you have num cost 1 over 0, and all these things. Pi, 2 pi, right? This is 2 pi power, float size, and you have all of these things. So the EM algorithm, you now say for iteration in range up to 100, each step is for I in range n, for k in range k, gamma I k, pi k, multivariate. So this I have bearing with the formulas we've seen before. That is the each step. If you follow all these steps that were first described up here, I mean this now. So all these things, that's what you have. And for the maximization steps, you have all these gamma I k and everything. That's what is actually being explained in all these places. So you have all the gamma and everything, and you can now predict the cluster assignment. So labels np.agmax gamma ag is 1, and then you run this, and then it gives you okay, it's still working at night, done. All right, so here you have three distinct clusters like that because you're working with synthetic data that seems to do better than even real data. But of course, it's synthetic just to give us an idea of what to expect. So that talks about the expectation and maximization, steps. So comparison between Gaussian mixed model and K-means clustering. Um, so for cluster shape, for K-means it is spherical, for GMM it is elliptical via covariance matrix. Then for membership, K-means is hard, but GMM is soft. Hard because you have clear clusters. But here every data point, like hard because every data point belongs to a unique cluster. But in GMM, which is soft and probabilistic, every data point belongs to every cluster with a given probability. Then talking about the distance metric, for K-means it is Euclidean in nature, and for GMM it is likelihood. Since we are talking about Gaussian density, which is probabilistic. Then for covariance handling, K-means assumes identity matrix, while GMM takes full covariance. For estimation algorithm, K-means uses Lloyd's algorithm, while GMM uses expectation maximization algorithm. So applications of GMM now, we can use it in computer vision for image segmentation, background subtraction. We can use it for speech recognition. The domain in speech recognition, things like speaker identification and verification. We can use it in finance, where we talk about modeling stock returns distributions. We can use it in biology for gene expression clustering. We can use it for anomaly detection, for rare event detection, and probabilistic modeling. All right. So, in conclusion, mixture models provide a flexible, powerful framework for modeling nonlinear overlapping clusters in data using soft probabilistic assignments. Through the expectation maximization algorithm, GMMs iteratively refine their understanding of the data structure, making them a robust alternative to K-means in real-world applications. All right. So if you want to do soft clustering, you want to use Gaussian mixed models because it is probabilistic in nature, right? That's how it has been for this. Let me know how helpful this has been for you, and if there's something you'd like me to try out. If you have subscribed already, thank you very much. If you have not, go ahead and subscribe, and of course, hit the notification bell so you can always get alerted every time a new video is released. You can also become a member of this channel. Just click on join, and you find membership options and the attached benefits you stand to gain, like that. So like and share this video so that more people can have access to the content I have going on here. Till I come your way again, keep doing data right. Bye.